In this fifth and last item on the first test of 2015 spring, we've got a reinforced concrete post that is 4 foot high. The total axial force that's applied to it of 150 kips, forcing compression, and we're told that we have a total steel area of 1.767 square inches, steel strength of 60 ksi, elastic modulus there, concrete area, that's the net concrete area, because note we got an 8 by 8, and actually there's a slight typo here, that should be 62.23 to get exactly 64 square inches when we add it to the steel, but we'll use what's printed there. And then we have a concrete strength of 4 ksi, concrete elastic modulus of 3600 ksi, and of course then again the length of the steel post. So we're supposed to find the axial stress in each material of this integrated steel and concrete structural member. And so if we come down and create a free body diagram by cutting off the top of the post, here's our 150 kips, and we've got our axial force in the concrete, and then as an aggregate the axial force in the steel. Since we're assuming that this is a concentrically applied load, we do not need to model each individual steel bar. We can take them as one big old lump sum. And of course this very simple equilibrium equation is going to tell us that the steel and concrete work together to support this 150 kips of total applied force. So that's our first and pretty important first step here. Ooh, hey, that's the only equilibrium equation. We've got two unknowns, one equation. That tells us that we are statically indeterminate, and if you cared, to the first degree, meaning we have one more unknown than we have equations available to us. Sum of forces of the x, sum of moments, none of that is going to be at all useful here. So we have an indeterminate system, and that means that the only way we can find the axial stresses, and really that axial force from which to get the axial stress, is by to look at deformations and displacements. Right, so that's the key next step here. Because we're going to have to get a compatibility equation eventually, and that's what's going to unlock this problem for us. Right? And so in this case, our displacement downwards at the top of our post is going to end up equaling the same thing as the deformation in the steel and deformation in the concrete. Those two are bonded together, so as the top of the column shortens down, then both the steel and concrete will go through the exact same. And that's going to be our key, because in the elastic region, we'll have to assume for now that it is elastic and then check it later, and this delta will equal ML over AE. Right? So this thing right here, that was our compatibility equation. Right? And the force deformation relationship was this guy right there, delta equal N over AE. So L is the same for both. But the moduli and the areas certainly are not the same. So L's will cancel out, and our axial force in the steel, that's the total steel, that's important here, it's going to be the ratio of the modulus of rigidity of the cross section, and that's EA for the steel over EA of the concrete times NC, right? And let's see here, EA of the concrete will equal 3600 KSI times our area of 62.3 square inches, and so that'll equal 224,400 kips, and EA for the steel, now I wish I would have reversed that order here, but that's 29,000, that's 1.767, that equals 51,243 kips. Right, so we want to plug those in, and we find out that then axial force in the steel is equal to 0.228 or so of the axial force in the concrete. That means we can go back to now our equilibrium equation to solve for our axial force in the concrete. Some of those two had to be equal to 150 kips. So N steel plus N of the concrete equals now 0.228 NC plus NC equals 150. So therefore, the force in the concrete is equal to 122.1 kips, and the force in the steel is going to end up being 27.9 kips. And we don't know yet if that's elastic or not, so that's along the way to making sure that our model is appropriate, right? So that's elastic behavior that we're assuming, right? And so now we're going to check that as well as do our calculation for the axial stress and hope that it is all okay. And so then that will just be for the steel, axial force in the steel over the area in the steel, then it's going to be our 27.9 kips over our total, because remember NS was all of the bars together, and that will work out to be 15.8 KSI, that's in compression, and that is less than the strength of the steel, so that's good. We haven't violated that condition. We're not told whether that 60 KSI is yield stress or not, but I can tell you grade 60 steel for reinforcing bars these days is common. That is the yield stress that we were provided. You wouldn't have any way of knowing that from a practical standpoint. That was the only information given to you. Sigma of the concrete is equal to N of the concrete over the area of the concrete. That's your 122.1 kips. Wow, most of the concrete is what carries most of the load. That's kind of interesting to know. Divided by the area, 62.3 square inches. And alright, so that's 122.1 over 62.3. That's 1.96 KSI compression, and that is less than 4 KSI. That's given to us as the concrete strength and as a check mark as well. What you'll learn in the reinforced concrete design class is how to evaluate these numbers in a design context where we allow for uncertainty and variability, and you'll see a slightly different kind of perspective, but it all stems ultimately from where we're looking at things right now.